Welcome to our exploration of counting. Today we're diving into the fascinating world of combinatorics, where we figure out the number of ways specific events can happen. This isn't the kind of counting that you might teach in kindergarten. It's much more intriguing. Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Let's start with something sweet. Imagine that you are at an ice cream shop. How many different 2-scoop ice cream cones can you make using just 2 flavors? We'll tackle this tasty question shortly. Next, consider a delivery truck navigating the city. How many different routes can the driver take? And what if the route includes a mandatory lunch break at a popular spot on the corner of 5th and Broad? This scenario adds complexity and opens up an array of possibilities. Moving beyond desserts and delivery routes, the principles of counting are crucial in probability, much akin to highbrow fortune telling. For example, tossing a coin twice yields 4 possibilities. Heads heads, heads tails, tails heads, or tails tails. What are the chances both tosses land on heads? With one favorable outcome out of 4, the probability is 25%. While probability features in games and predictions, it also plays a vital role in physics, from statistical mechanics to quantum mechanics. However, today we will be focusing purely on counting, starting with the basics. Consider Sophia, who owns 3 shirts and 2 skirts. How many outfits can she create? You might initially think 5, since 3 plus 2 is equal to 5. This would be correct if she were choosing between 3 identical blue shirts and 2 identical white shirts, because she can only wear 1 shirt at a time, and therefore has 3 plus 2 equals 5 choices. This result is called the principle of addition in combinatorics. Since shirts and skirts are chosen independently, the total number of outfit combinations Sophia can create is actually greater than what you might initially think. For illustration, let's consider her wardrobe. She has 3 shirts, 1 green, 1 pink, and 1 teal. She also owns 2 skirts, 1 yellow and 1 blue. Starting with the blue skirt, Sophia can match it with either the green, pink, or teal shirt, resulting in 3 unique outfits. But this is just the beginning. Each additional skirt she owns can also be matched with any of the 3 shirts, multiplying her options. With just 2 skirts, this already gives her 6 possible outfits. This scenario perfectly demonstrates the principle of multiplication in combinatorics. We can expand the possibilities further. Imagine adding another item, like this awesome camouflage shirt. When we delve into the question of how many, we encounter different methods of counting, each with unique rules and outcomes. Today we'll explore these through the universally loved medium of ice cream. First up, consider the scenario where order matters and repetition is allowed. Imagine creating an ice cream with multiple scoops. With 2 flavor combinations, chocolate and vanilla, and 2 scoops, how many different combinations can you concoct? If you choose just 1 scoop, the answer is simple. It's either a scoop of chocolate or a scoop of vanilla. But with 2 scoops, the permutations increase to 4. A scoop of chocolate, followed by a scoop of vanilla. A scoop of vanilla, followed by a scoop of chocolate. 2 scoops of vanilla, or 2 scoops of chocolate. Because with a cone, you can only eat from the top, so order matters. Some people prefer to eat one before the other. That's why I've chosen ice cream cones to represent situations where order matters in counting. Next, let's consider bowls of ice cream, where order does not matter, but repetition is still allowed. Here, you're not concerned with the sequence of scoops. Whether you scoop a scoop of chocolate or a scoop of vanilla first, it doesn't matter once it's in the bowl. With the same 2 flavors as before, chocolate and vanilla, the possibilities reduce to just 3. A bowl with 2 scoops of vanilla, a bowl with 2 scoops of chocolate, or a bowl with 1 scoop of each. The arrangement of scoops in a bowl can be rearranged by simply rotating your bowl or moving your spoon somewhere else. Order is irrelevant when it comes to ice cream in a bowl. Moving to scenarios where repetition is not allowed changes the game. If order still matters, you end up with 2 distinct cones, vanilla chocolate or chocolate vanilla. However, if order doesn't matter, you're left with just 1 possible combination, a single scoop of each flavor. We can organize these 4 cases into a table of 4 quadrants. On the horizontal axis, we consider 2 cases, where order matters or not. On the vertical axis, we consider the 2 cases where repetition is allowed or not. The upper left quadrant, where order matters and repetition is allowed, will hold the 4 unrestricted 2-scoop ice cream cones. By unrestricted, I mean there is no restriction on repeated flavors. 2 scoops of chocolate or 2 scoops of vanilla is allowed. The lower left quadrant, where order matters but repetition is not allowed, will hold the two unique flavored 2-scoop ice cream cones. By unique flavored, I mean that each scoop must be a different flavor. No chocolate chocolate or vanilla vanilla cones here. The upper and lower right quadrants of our table will hold bowls of ice cream, since these are the cases where the order does not matter. In the upper right quadrant, we will place the 3 unrestricted 2-scoop bowls, and in the lower right quadrant, we will place the single unique flavored 2-scoop bowl. These examples might seem straightforward with just 2 scoops and 2 flavors. But what if we increase the options? Say 3 scoops and 4 flavors. That's when counting the number of ways becomes less intuitive and more complex. To tackle these more challenging scenarios, I'll introduce you to the formulas and methods that help compute these possibilities efficiently. Let's begin with the top left quadrant of our conceptual table, where order matters and repetition is allowed. In our first example, where repetition is allowed and order matters, we see a classic example of the application of the multiplication principle of combinatorics. Let's break it down with our simple ice cream scenario. Imagine you're choosing a 2-scoop ice cream cone from 2 available flavors. How many options do you have for the first scoop? 2. And for the second scoop? Well, still 2. Because repetition of flavors is permitted. So the total number of combinations for your cone is 2 times 2, which is 2 squared, which is 4. That's 4 different ways to build your ice cream cone. Now, what happens if we expand our options to 3 scoops and 3 flavors? You'd have 3 choices for each scoop, making the total combinations 3 times 3 times 3, which is just 3 cubed, which is equal to 27. 27 different ice cream cones. To generalize, if you have S scoops and F flavors, the total number of combinations is expressed as F raised to the power of S. For instance, a cone with 3 scoops from the 31 flavors at Baskin-Robbins could be arranged in 31 cubed ways, which is a total of 29,791 different combinations or different ice cream cones. It's a vast array, so you might think twice before trying one of each. In the previous scenario, we always had the same number of choices for each scoop. However, when repetition is not allowed and order matters, each subsequent choice becomes increasingly limited. For example, if the first scoop has 2 flavor options, like chocolate or vanilla, selecting one reduces the choices for the second scoop to just 1 remaining flavor. Let's illustrate this with our 2-scoop, 2-flavor example from earlier in the video. If we choose chocolate first, then vanilla is the only option left for the second scoop. And if we choose vanilla first, then the second scoop has to be chocolate, resulting in 2 choices for the first scoop and 1 choice for the second scoop. 2 times 1 equals 2 choices, or 2 unique combinations. Now, what if the options are expanded to 3 flavors, but we stay limited to just 2 scoops? The first scoop gives us 3 choices. After choosing 1, only 2 flavors remain for the second scoop, giving us 2 choices, followed by 1 choice for the final scoop. That gives us 3 times 2 times 1 equals 6 possible cones. This kind of sequential reduction in choices is captured mathematically by what's known as a factorial. For 3 flavors and 2 scoops, it's calculated as 3 factorial equals 3 times 2 times 1 equals 6. This factorial concept becomes even more interesting with more flavors. For instance, if 4 flavors are available, but we can only choose 2 scoops, the calculation would be 4 choices for the first scoop and 3 choices for the second, resulting in 4 times 3 equals 12 unique combinations. However, if we were choosing all 4 flavors in sequence, the factorial of 4 equals 24 different combinations. 4 times 3 times 2 times 1. In terms of formulas, with F representing flavors and S representing scoops, just as before, the number of ways to assemble the ice cream is given by F factorial divided by F minus S factorial. The division is simply removing from the count the choices we would have if we had as many scoops as flavors. So we first compute as if we had as many scoops as flavors, and then divide by the complementary factorial to restrict the number of scoops. So for example, here we would have 4 factorial divided by 4 minus 2 is 2 factorial. That's 4 times 3 times 2 times 1 divided by 2 times 1. The 1 and the 2's cancel, and we're just left with 4 times 3 equals 12. Let's return to Baskin-Robbins and imagine that they have restricted us to no repeat flavors on a 3-scoop cone. The combinations possible plummet from a staggering 31 cubed, which was equal to 29,791 from the exponential case, to a factorial-based calculation of 31 factorial divided by 31 minus 3 factorial, which is equal to 31 times 30 times 29. Since 31 minus 3 is 28, we're going to divide by 28 factorial. So we can cancel everything out from here. And so we get 31 times 30 times 29. And what's that equal to? That's equal to 26,970 different combinations. Still, quite a hefty number of flavor permutations. Before moving on to the ice cream bowls section of our table, let's talk about the number of ways a word can be rearranged. How many 3-letter words can you make from the letters T, O, and M? And no, they don't all have to be real words, like Tom. They can be nonsense words like MTO. The best way to solve a problem like this is systematically. We will order our letters from lowest to highest. M, followed by O, followed by T. Next, we will imagine 3 blanks. These are the first, second, and third letters for our proposed word. How many choices do we have for the first slot? We can choose the M, the O, or the T. So 3 choices. Let's assume we pick T. For the next slot, we only have 2 choices, the O and the M. So let's pick O. I guess you know where I'm going with this. For the last slot, there's only 1 letter choice remaining, the M. By the multiplication principle of combinatorics, that is 3 times 2 times 1 equals 6 possible words. What are these words? Let me show you a systematic way to arrive at all the possibilities using a tree diagram. Start by spacing all 3 letters out vertically as follows. M, O, T. Starting at the top, construct 2 branches adjacent to each of the 3 letters. Why 2 branches? Because there are 3 minus 1 letters left. Now fill in each of the 2 branches with the 2 letters not yet listed in each row. Next, draw a single branch next to each letter and add the 1 letter missing from that row or path. Finally, write all the letters in the path to get all 6 words. If we think of this word rearrangement problem like we did about ice cream cones, where instead of scoops we have slots for letters, then we can recover the same factorial equation we saw for scoops of ice cream in a cone. Similarly, if we have more letters to use than slots to put them in, then we can use the full formula of number of ways equals f factorial over f minus s factorial, where instead of flavors, we will use number of distinct letters, and instead of scoops, we will use word length. What happens if we have repeated letters, like in the word Bob? Let's make another tree diagram, but let's temporarily distinguish between the 2 B's. I'll make one an uppercase B and the other a lowercase. We can use the same tree diagram from before, where the T is replaced by the uppercase B, and the M is replaced by a lowercase b. Since there is no difference between the 2 B's, half of these words are duplicates, and so the simple factorial formula we used before overcounts. But by how much? We need to divide by the number of ways to permute uppercase B and lowercase b, so 2 factorial. Thus we divide the count from before by 2, which is why we saw half the words as duplicates. Let's apply this to a more complicated word with a lot of repeated letters. Mississippi is a long word with 4 repeated S's, 4 repeated I's, and 2 repeated P's. This word has 11 letters, so we start with 11 factorial. This, however, overcounts, so we divide out 4 factorial for the repeated S's, and another 4 factorial for the repeated I's, and finally 2 factorial for the repeated P's. So the number of ways is given by I will leave it to you to check that this is correct. So get out your Scrabble boards and start arranging. What use is this for our ice cream problems? Well, in order to answer that, I must first tell you about committee problems. Okay, how many ways can we form a student committee of 2 students from a class of 5? Well, start with the 5 students. Then add 2 O's for the 2 people on the committee. It doesn't matter which we choose, so we may as well choose the first 2. Next, add an X underneath each member of the rest of the class to designate them as not on the committee. I leave it to you to prove to yourself that the committee question is the same as asking how many ways we can rearrange the word ooks. We know how to answer this. It's just 5 factorial divided by 2 factorial. The 2 factorial is for the O's, and we also need a 3 factorial for the X's. So the number of rearrangements and the number of possible committees is then, well, this will just reduce to 5 times 2, or 10 possible committees. In combinatorics, these committee problems are called in choose K. It's usually written like this, in choose K. Our problem was 5 choose 2. We write in choose K, the formula for it anyways, is written like this. In choose K is equal to in factorial divided by K factorial, all times in minus K factorial. So simply substitute n equals 5 and k equals 2 in the formula, and voila. Okay, let's dive back into our ice cream exploration. Consider this. How many different 2-scoop ice cream bowls can you create from 2 flavors when no flavor is repeated? Since the order in a bowl doesn't matter, that might seem like a simple question because there's obviously only one possible combination. Let's check if our formula holds up. With 2 choices and no repetitions, our calculation is 2 factorial divided by 2 factorial times 0 factorial. Interestingly, 0 factorial is defined as 1. Surprising. But it's a standard mathematical convention, and you'll just have to trust me on that. According to this formula, we indeed end up with one unique bowl. I don't think, however, that we've really showcased this method well, so let's return to Baskin-Robbins. How many unique flavored 3-scoop bowls can we concoct from their array of 31 flavors? Applying our formula, we calculate it as 31 choose 3, which is 31 factorial divided by product of 3 factorial and 28 factorial. Simplifying this, we get 31 times 30 times 29 divided by 6, which equates to 31 times 29 times 5. What do we get then? Doing the math, that's 155 times 29, which is equal to 4,495. While still a large number, it's significantly fewer than the 26,970 unique flavored ice cream cones or the staggering 29,791 unrestricted cones we discussed earlier. And with that, we're almost entirely through our ice cream scenario table. When order does not matter and repetition is allowed, we adopt a clever labeling scheme known as stars and bars. Although I'm not certain of its origin, the earliest usage I know of is from Paul Ehrenfest in 1914, who used this technique to derive Max Planck's formula for distributing energy among single-frequency resonators. Let's apply this to the last quadrant in our table, unrestricted 2-scoop ice cream bowls. We use an O to represent a scoop of ice cream and a vertical bar as the partition between flavors. In this system, only one partition is needed. If the O is to the left of the partition, it represents a vanilla scoop. To the right, it represents a chocolate scoop. For example, 2 chocolate scoops would be represented as a partition followed by OO, and one of each flavor as O partition O. If we label the vertical partition as L, we could describe the 2 chocolate scoops as Lu, and 1 scoop as the word Olo. The number of ways to arrange 2 unrestricted scoops from 2 flavors can be equated to rearranging the letters in Olo. With 3 positions and 2 repeating elements, this calculates to 3 factorial divided by 2 factorial, which is equal to 3 different combinations, matching our earlier result. All right, one final visit to Baskin-Robbins. If we scale this up to a more complex scenario with 3 unrestricted scoops from 31 flavors, we face a new challenge. The configuration could be represented as a sequence with 3 O's and 30 L's, indicating scoops and partitions respectively. The mathematical challenge then becomes calculating the permutations of OOLOL, which is 31 factorial divided by 30 factorial and 3 factorial. And that is equal to 11 times 16 times 31, which equals 5,456 possible combinations. I think that is still too much to try every combination. Let's summarize the methods described here as it relates to our table. In the upper left quadrant, dealing with counting problems where order matters and repetition is allowed, the number of ways is given by an exponential. For our ice cream example, the number of possible unrestricted flavor combinations, S scoop cones from F flavors, is given by F raised to the S power. In the lower left quadrant, in which order matters but repetition is not allowed, the number of ways is given by a factorial. For our ice cream example, the number of possible unique flavored S scoop cones from F flavors is given by F factorial divided by F minus S factorial. The rightmost quadrants can be calculated using a labeling scheme applied to a word rearrangement problem. The upper right quadrant, where order doesn't matter and repetition is allowed, uses stars and bars for calculation. The lower right quadrant, where order doesn't matter and repetition is not allowed, uses the method of X's and O's, or in choose K. You won't be able to crack every counting problem that you might encounter with these methods, but it is a good start. I hope you have enjoyed this intriguing journey through the world of combinatorics, exploring how simple principles can unravel complex counting challenges. Remember, this is just the tip of the iceberg when it comes to the power of combinatorics. Don't forget to like, subscribe, and click the notification bell so you don't miss my future explorations of mathematical and physics concepts. And remember, stay curious. Does anyone want some ice cream?